All right, we're going to close up Unit 4, which is all of our probability, Chapter 5 and Chapter 6, with binomial and geometric random variables. Okay, so this is more probabilities, but these are variables that take on certain conditions, and so then they're called binomial and geometric. And we're going to talk about the difference between the two, and we'll talk about how to find those and how to interpret those probabilities as well. So some pretty crazy formulas, they'll be given to you on your formula sheet, but super easy to calculate in the calculator. So we're going to get really used to identifying which one is which and then plugging it in the calculator, and you should be able to solve these questions in no time once we've figured out which one it is, whether it's binomial or geometric. All right, let's go ahead and get started with binomial then. A binomial setting arises when we perform n independent trials of the same chance process and count the number of times that a particular outcome occurs. Okay, so we're going to break this down into 4 things that we want to check to see if it's binomial. So the first thing we're looking at is binary. Okay, so binary means a this or that situation, one or nothing. Okay, so we're looking for, in this trial, is it counted as a success or a failure? So flipping a coin, we either get a heads or we don't get heads, we get tails, right? So is my option just one or the other? If that works, then we check the next thing, are they independent? So if I flip one of them, does it affect the next one, right? We're talking about independence in our probabilities. So just like when we were talking about, does the condition affect that probability or not? So are they independent? And they must be independent of each other. If they're independent of each other, the next thing we look for is the number. So the number of trials must be fixed. So this is, I'm going to flip a coin 20 times. Not, I'm going to flip a coin until I get 20 heads. It's just, I'm going to flip a coin 20 times. So if we know when we're going to stop our experiment, when we're going to stop our simulation, then it has a fixed number of trials. And then we're looking for same probability. So is there the same chance for each trial? Okay, so a coin toss, like we already said earlier, would be very much a binomial situation. It is binary. We either get heads or we don't. Okay, they are independent. If I flip the coin and I get a heads, that does not affect whether I'm going to get a tails or a heads the next time. If I flip it for a certain amount of times, like I just said, if I flip it for 20, now it's binomial. If I flip it until I get a certain result, now we're talking about geometric, and we'll jump into that. And I have the same probability of either one. I get 50% whether I get heads or whether I get tails. So that would definitely be how we check for a binomial setting. Let's go ahead and do that. Determine whether the given scenario describes a binomial setting. Justify your answer. So part A says, genetics says that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has probability 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So let's talk about our 4 settings. So binary. Do we have a this or that situation? Okay. Are we going just between a success or a failure? We either get this or we get that. Do we have independence? Do we have a fixed number of trials? And do we have the same probability for each one? So if we look at those, we check all of those, then we are good to go. The success would be having type O, and the failure would be not having type O. Okay, so we're not comparing type O to all the other types. We just want to know, do they have type O blood? So they either do or they don't, right? Can't have both. Therefore, they are also independent. It already said it in the problem, but knowing one child's blood type is not going to change whether the other child gets the blood type or not. Okay, so they are independent. We have a fixed number. We're just going to have 5 kids. It's just already too many. And we're going to have the same probability. It even says each child has a probability of 0.25. So it's telling me right there, everything was in there. Okay, we've got independence. We're going to have exactly 5 children, the same probability, and we're just looking at one type of blood. So type O or not. So we hit those binomial settings. Let's check the next one. Determine whether the given scenario describes a binomial setting. Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. So we're looking at aces. So we've hit the binary setting. We either get an ace or we don't get an ace. Okay. We have exactly 10 cards, so we have a fixed number. And but when we look at independence, this is where we actually are going to fail, because if I flip over a card, if I have a deck of cards and I flip one over and I get an ace, well, that's now one less ace in my stack of cards, which means that now the probability of getting an ace has changed. So whether I get an ace or not does affect the probability of me continuing to get aces. So therefore, they're not independent of each other. And I also don't have the same probability because the probability is changing every time I take a card, right? So this one is not a binomial setting. Once we know it's a binomial setting, we're going to calculate the probabilities. We have a very convoluted formula here, which is broken down. It's got factorials, it's got exponents, it's got everything. The formula is on your formula sheet, and the only time that you will have to use the formula is in a multiple choice question where it's asking you to pick which formula would be correct. So they're literally just going to plug in all of these numbers, and you just need to see which one is matching the scenario. So we're not going to spend a lot of time on understanding what this formula says. We're going to figure out what the variables represent. All right, so suppose that x is a binomial random variable. So we've determined that it is a binomial setting. N is the number of trials. P is the probability that we're given, and K is the number of successes. So this would be the number of times that we want something to happen. And then this is our formula, and that's what we're just going to plug in, okay? This part right here, this is N choose K. This is not a fraction. This is a combination, and you would calculate it either this long way or in your calculator. But again, we're not going to pay so much attention on how to use the formula. If you're a big formula person, I will show you later, just come see me, but we're not going to spend a lot of time because we're going to use the calculator to actually do it a lot faster. But we are going to look at how to plug in those numbers. So we're going to look at an example, and we're going to let everybody else solve it for us, but we are going to focus on how it was plugged into the equation, okay? So this is the genetics one with the type O blood. So we have the same scenario. Each child has a probability of 0.25 of having type O blood. We're going to have 5 children. X is my random variable, the number of children with type O, and we want to find the probability that we get 3 children with type O blood. So let's look at it plugged into our equation, okay? So since it's binomial, n is 5. That's the number of trials, the number of times we're going to do it. So that's 5 children. And the probability is 0.25. So we're going to plug that in. We have the probability that x equals 3. That's given to me right up here, all right? Or if it was in words, it said find the probability that there are that 3 children have type O blood. So we would say x equals 3. And 3 is our successes. That's the number of times we're looking for. So out of the 5 children, 3 of them are the ones we're looking for. We take the probability to the number of successes, and then we do 1 minus the probability to the number of failures, or the ones that are not happening. So because we have a total number of trials of 5, then if 3 of them are successes, 2 of them are failures. All right. So this first part, would be in a multiple choice question that wanted to make sure that you knew how to plug it into the formula, okay? If you also put this on an FRQ and then solved it with your calculator, this would give you those kind of bonus points in case you messed up something on your calculator. You might get points for having the right formula, because then they would think, oh, well, they understand what they're doing because they plugged it into the formula. Again, you don't need to memorize the formula. It's on your formula sheet. So you don't have to memorize it. Just use it. Just know what those K's mean. So K is my successes. All right. We've got P for my probabilities. And then we just have N for my number of trials. That's it. If you remember what N, P, and K are, then you can plug it in because it's always going to be given to you. Okay, so when they do all the math that we don't feel like doing, we get a probability of 0.08789. So if I were to interpret this, there is about an 8.8% probability, or a percent chance, whatever, 8.8% probability that exactly 3 of the 5 children have type O blood. Okay, so you're just taking your scenario, right? They got 5 kids, they're looking for 3, and putting your answer into a sentence. All right, so same scenario. But this time we're asking a different question. Should the parents be surprised if more than 3 of their children have type O blood? So let's take a look at that. So I want the probability of more than 3, okay? So if I'm doing more than 3, and I only have 5 children, that means they're either going to get 4 children or 5 children. So I would be doing the formula twice and then solving and adding those two together. So I get 0.01563. There's only a 1.5% probability of having more than 3 children with type O blood, so that would definitely be surprising. Remember, our threshold is usually about 5%. If anything is more than 5%, we're like, it's probably going to happen. Alrighty. All right, now let's look at how to use a calculator, because that's the key thing. So we're going to calculate these probabilities with our calculator so we don't have to use that stupid formula. So you're going to go to second vars on your calculator. And we've been here before when we were doing normal calculations and things. So we're in second vars and we are looking for binom, and you have PDF and CDF, okay? So PDF is going to occur when we are testing that something is equal. So the first problem that we did when we had x equals 3 was a binom PDF. And then when they put in the calculator, you see that you get the same result that they did using the formula. Alrighty, N is your trials, P is your probability. So it's the same thing that's labeled in the formula too. So N is trials, P is probability. And then if we have a less than or a greater than or something like that, then we're going to use CDF. So binom CDF is when I have a comparison. Okay, so P is when it is exactly equal to a value. CDF is when I want something less than or greater than something. So keep in mind that your calculator, just like when we did normal distributions, is always calculating less than. So you need to figure out what number you're going to put into your calculator based on what the problem is asking. So for the second part of that type O problem, they wanted more than 3 kids. If my calculator is calculating less than, then that means if I put in 3 in the calculator, that's telling me 3, 2, or 1 kids. So then I need to do 1 minus that because I'm looking for the greater than 3, okay? If it said the probability that x is greater than or equal to 3, now that means I want 3, 4, and 5, which means in my calculator I should be putting in 2. Because if I have 3, 4, or 5 kids, then that means the calculator can solve 1 or 2, and I will subtract from 1 for that. So if I find the probability of getting 2 or less kids, then the not of that, the complement of that, is going to be what I'm looking for, the 3, 4, or 5. Okay? So keep that in mind. If it's a regular old greater than symbol, you can just put that number in the calculator, but you still have to do 1 minus, okay? Every time 1 minus if it's a greater than. If it's a greater than or equal to, you need to put the number less than that it's testing and still do the 1 minus, okay? So greater than, just put that number but do 1 minus. Greater than or equal to, put the number that is below it and still do 1 minus afterward. All right, so let's go ahead and solve one with the calculator. A local fast food restaurant is running a draw of 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates 1 card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. On the first day of the promotion, 250 customers place lunch orders. Find the probability that fewer than 10 of them win a free lunch, okay? So before we even throw up this answer here, let's break this down. We are looking for the probability that less than 10 of them win a free lunch, okay? So I'm looking for 1, 2, 3, 4, 5, 6, 7, 8, or 9, alrighty? So when I'm plugging this in the calculator, because I have less than 10, I don't want to type 10 in because the calculator is going to include 10. I need to find 9 or less, right? That's going to be the same thing as being less than or equal to 9, because if it's less than 10, it's got to be the 9, okay? And this is because we're doing whole numbers. I can't have 9.8 of a person, so I can just switch it down to 9. All right, so we're going to keep that in mind when we plug it into our calculator. Our number of trials is going to be 250. That's my n, okay? And let's go ahead and plug that in. My k, if I was using the formula, would be 9. All right, let's go ahead and check. So they're using y in this case, whatever. They're defining the random variable. Okay, that is important. If you're going to start writing this down in your work on your FRQ, make sure you define what your random variable is, which is just what it's trying to find. So let y be the number of customers who win a free lunch. We have n equals 250 and p equals 4 out of 52. Alrighty, where are they getting this probability? It's a deck of cards. It's showing a regular old deck. So there are 4 of every card in there. So 4 out of 52 would be a 3. They're trying to draw a 3 card. All right. So notice we put 9 in there. Binom CDF because it is a less than problem. It's not equals to 10. We want fewer than 10. And we get 0.006. All right. So 0.6%. Very small chance. So on that day, only 9 customers won a free lunch. Do we think that the computer program is flawed? Well, we just calculated that winning, like getting 9 people or less, right, less than 10 people would be a 0.6% chance. So do we have convincing evidence that the computer is messed up? Absolutely. There was only a 0.006 probability that fewer than 10 customers would win a free lunch if the computer program was working. So since it's a really small probability, the computer program must not be working, because that's kind of wild that we would actually get something that has a very low chance of happening. All right, last thing with binomial settings is finding the mean and standard deviation, just like we just did with random variables last week. So we have a formula for it. It's on your formula sheet, and it's a pretty short one. Your mean is also called the expected value. You take your number of trials times the probability, okay? So whatever our probability is, multiply it by how many times we're going to try it, and that's what I would estimate it to happen, right? That's my expected value. Just make sure we have the right notations, and we're good to go. Standard deviation also has a formula, way less complicated than a lot of our other standard deviations formulas, so we could actually just calculate it ourselves. And again, the formula is going to be given to you in your formula sheet. So we take the number of trials times the probability, and then times it by the probability of it not happening, so 1 minus that probability. Only works for binomial distribution, so you can't just use this mean and standard deviation for everything. This is only when you've determined that is a binomial situation. All right, let's go ahead and do that. Let's find our mean and our standard deviation. All right, assume that each of the 21 students in this AP class, they did a bottled water versus tap water activity, and they were just guessing, so there's a 1 out of 3 chance of each student identifying the cup containing bottled water correctly. So there's some missing information here. There were 3 cups of water. 1 of them was bottled and the other 2 were tap water, and they had to determine, or they had to guess which one they thought was bottled water or tap water. So we're assuming that none of them were able to tell, and so then if you can't tell at all, if nobody can tell what type of water it is, there's a 1 out of 3 chance I'm going to guess the right cup, right? So calculate and interpret the mean of x, where x is the number of students who make a correct identification. Okay, so let's find that mean. We have the number of trials, 21 students. The probability is 1/3. 1/3 of 21 is 7. So if I'm interpreting it, if all the students were just guessing and they repeated the activity many times, the average number of students who guessed correctly would be about 7. Okay, so we're just taking our estimated value. Find the standard deviation, so we're going to calculate that, use our formula, plug it all in, so number of trials times the probability of not happening is 2.16. So if all the students in the class were just guessing and repeated the activity many times, so you're taking your scenario, don't forget saying repeated many times, because this is a probability, so if we did it a lot of times, the number of students that identified it correctly would typically vary by about 2.16 from the mean. Still regular old standard deviation interpretation. It is how far something varies from the mean. All right, that was a lot for binomial because it's got a lot of things to keep in mind. Geometric, we're going to go way faster. So a geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. So remember back in binomial, we were just getting a certain amount of trials. We were just going to see how many we could get out of a fixed set. A geometric setting is how many times do I have to do it? How many trials do I need until I get the result? And the probability must be the same. So it doesn't have nearly as many things that we need to calculate or look at like binomial because that's your difference, is you're going until you get something, not you're going a certain amount of times. Alrighty, and let's go ahead and look at our formula for this one. So same principle, much easier formula. K is the number of successes, so the number of times it's going to take us to get there, or number until we get somewhere, and then P is our probability. Again, it is going to be on your formula sheet. So let's go ahead and look at how to calculate those. Alrighty, Mr. Lochelle's class decides to play the lucky day game. A student will be selected at random from your class and asked to pick a day of the week. Then your teacher will use technology and to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random and repeat the process. The game continues until the student correctly picks the lucky day. Let y equal the number of homework problems that the class receives. Okay, so if the kid gets it, then they only get one problem, but you keep going, so every time someone's wrong, right, that's going to tell us how many homework problems we're going to get. So we're going until we get a certain number. We're not saying we're going to try it 20 times. We're going to go until we get this value. Okay, so part A says find the probability that the class receives exactly 10 homework problems as a result of playing the lucky day game. So let's look at plugging it into the formula. Oh, JK, let's look at the calculator function. So if I plug this into my calculator, we want to know exactly 10. We're going to go to the same spot, second vars. Now we're looking for geometric PDF, so we want it to be equal to 10. So we're doing the probability that x equals 10, and our probability is a 1 out of 7. Where are we getting that 1 out of 7? Because they're picking a day of the week. It's only 1 out of 7 days of the week, and it's the same probability, right? So plug in that into our calculator, and we get 0.0356. Same thing for binomial. If I want something less than or greater, I'm using CDF. And again, the calculator is always calculating less than or equal to. So make sure you change your number in the calculator based on what the problem is asking you. All right, mean and standard deviation also has a formula, again, on your formula sheet. So the mean of a geometric distribution is just 1 divided by the probability, and its standard deviation is the probability of the square root of the probability of it not happening divided by the probability that it does happen. All right, let's go ahead and calculate those. So this is the draw 3, get a free lunch kind of situation. X is the number of customers it takes to get the first free order on a given day. Okay, so again, it's not I have this many customers, it's just how many customers is it going to take me until I get that first free order. So we have geometric now. Calculate the first calculate and interpret the mean of X. So we're geometric. My probability is 4 out of 52 again because I'm talking about drawing cards. So I just take 1 divided by 4 out of 52, which gives me 13. So it is expected that on average, it's going to take 13 people until someone gets a free lunch. Okay, so if the restaurant runs this lunch promotion on many days, the average number of customers it takes to get the first free lunch would be about 13. Standard deviation, same thing, plug it into the formula, and we get 12.49. And when we interpret that, if the restaurant runs this lunch promotion on many days, the average number of customers it takes to get the first free order will typically vary by about 12.5 from the mean of 13. That is a very big variation, right? So this is not very solid of a plan here that they have. Alrighty. That was your geometric and your binomial distributions. It's all formulas, okay, or calculator. The hardest part is understanding which one is which. But it's really not that hard because you just have to read your question. If the question says, I have a certain amount of trials and I want to know the probability that this happens out of those certain amount of trials, you have a binomial setting. If the question says, what's the probability that, or how many do I have to get until I get this result? Now it's geometric. That's your difference. Once you know the two, find your formulas on your formula sheet for your mean and standard deviation and plug them into your calculator. All right, that's going to be the hardest part, is interpreting the problem to figure out which one it is. After that, we use our calculator and we're golden. That's how we solve our probabilities. All right, so we have finished up Unit 4. We are all done with probability. Woohoo, because I think this is like the most convoluted unit of the whole statistics curriculum. So we're all finished with probability. We're going to wrap things up, and then we're going to jump into sampling distributions, and we're going to start tying everything that we have learned into one FRQ. So I hope you're ready for that. Let's go ahead and solidify those Unit 4 stuff, and we'll practice up with Chapter 6 this week. All right, as always, have a great rest of your day, and I'll see you back here when we start sampling distributions.